In the previous lesson, we were ready to call the basic saw function. But in order to make sense of what we are doing inside that function, it will help to go over the basics of waveforms and how we will be using them in our code. First, let's look at a sine wave. When we cycle through a waveform, it is like we are going in two circles. One will be a positive circle, and the second will be a negative circle. Between is neutral, or zero. Now let's take a look at a saw wave. This is very similar to the sine wave, except when it reaches the positive peak, it will jump to the negative peak and continue to rise up from there. Our representation is showing a start value of 0, peaks at +1, jumps down to -1, continues upwards to 0, and repeats the cycle again. Here we have a representation of the 32,000 samples per second we generate. Now let's place these samples on our waveform. A 1 Hz waveform will use up all 32,000 samples in 1 second. Here we show a representation of samples generated with the violet-colored vertical lines. I've greatly reduced the actual amount of samples for clarity. Horizontally, we sequentially move through the samples in time. And vertically, we represent each sample in amplitude. On the left, we can see a scale of values ranging from -1 to +1, with some intersecting points between the values and the samples. These intersecting points are the phase points in the waveform. What may become confusing here in a minute is the relationship between the phase value and the amp value of our sample. We increment the phase according to the frequency. The faster the frequency, the more we increment the phase value between samples. The more we increment the phase, the faster the amplitude of each sample increases in our saw wave. The frequency may get faster or slower, but we will always have 32,000 samples per second. So when the frequency goes faster or slower, we do not sequence through the samples faster or slower. We will always sequence 32,000 samples per second. As we increment the phase, it will always track from 0 to twice the value of pi, labeled here as 2 pi. Once we've exceeded 2 pi, the waveform and the phase starts over again. In the next several diagrams, we will be using a phase symbol. It is this one, a circle with a vertical line through it. In this example, phase equals 0. Up here, phase is less than or equal to pi. Down here, phase is greater than pi. And over here, phase is equal to 2 pi. Looking at this 1 Hz saw wave example, we can see one full waveform cycle using up all 32,000 samples. The basic oscillator will have a phase begin at 0, peak just before pi at value +1, then snaps down to -1 when the phase is greater than pi, and continues to climb in values from there towards 0. When phase is equal to or greater than 2 pi, it will restart the process again with phase equals 0 or some value close to 0. Now let's look at a 2 Hz example. Here again we see the 32,000 samples in a 1 second period, but now we have 2 full saw wave cycles rendered in that 1 second period, because the phase increment between samples has doubled. The first cycle's phase begins at 0, it peaks at +1 when phase reaches pi, then it snaps down to -1 when phase is greater than pi, and continues until it reaches a value near 0 again when phase is greater than 2 pi. Then phase continues from there, and the process starts all over again to do another full cycle by the time it reaches the 32,000th sample. Here is another example at 4 Hz. We can see the same pattern as before, but now we are fitting 4 full saw wave cycles inside a 1 second period using 32,000 samples, because now the phase increment between samples has quadrupled. We can keep increasing the frequency to cram more full saw wave cycles inside this 1 second period of 32,000 samples. But the more cycles we fit in that period, the less resolutions we will have between each sample. The slower frequencies gradually change from one sample to the next, resulting in a smooth transition. The faster frequencies will change values quicker between the samples, causing more aliasing or stepping of the increments. The only valid values our samples will have prior to storing them to the buffer are -1 through +1, as seen at the left of this diagram. But there can be millions of decimal values in between -1 and +1 because float values can have a very fine resolution between them. Working with these values may seem odd at first, but as we work with the samples more, it will become clear why this is an ideal range of values to work with. The important thing to remember about the sample values is they are amplitude values. They are eventually used to increase or decrease the voltage output that the digital analog converter will produce. Later on, we will see how we convert the sample values into 16-bit signed integer values as seen here on the right in blue text. 16-bit signed values can have a range of -32,767 through +32,767. After we convert the float value to a signed 16-bit value, we immediately cast the signed 16-bit value to unsigned 16-bit values before we save the value to the buffer. The unsigned 16-bit values will be sent to the digital analog converter, which converts the values into voltages. I will explain more later on, but for now we're going to stay focused on these waveform concepts, and the next lesson we will move on into the next function call in our code, basic saw.